Okay, picture this. You're walking down a really busy street.
Right.
And you're somehow effortlessly weaving through people, sidestepping things. Maybe you even reach out and grab a coffee cup without thinking, without spilling it.
Or you're driving your car, making turns, handling traffic. It feels almost automatic, doesn't it?
Exactly. How do we manage all that so smoothly without, consciously running calculations for every single step or turn?
It's a pretty amazing feat of perception, and yeah, we definitely take it for granted most of the time. Our senses are constantly feeding us just the right information to act effectively, to navigate safely.
Absolutely. And that's what brings us to our deep dive today. We're going into the fascinating world of how we perceive motion, how we perceive space, and we're focusing specifically on a concept called optic flow.
Sometimes called optical flow, yeah.
Yeah.
And our main guide here is the foundational work of Dr. James J. Gibson, especially his really influential book, The Senses Considered as Perceptual Systems. We'll also bring in some related research, too.
Right. And our mission, really, is to unpack Gibson's idea, which was pretty radical at the time. He argued that perception isn't about our brain stitching together tiny little bits of sensation.
No, quite the opposite. He saw it as an active process. We're actively extracting rich, meaningful information that's already there right in the environment, especially through patterns of light and movement.
So get ready for maybe a few aha moments about how you actually see and interact with the world. It might change how you think about simply walking around.
It really might.
Okay, so let's dig in. The traditional view in psychology, the one influenced by people like Miller, Helmholtz,
Yeah.
it often treated our senses like they were, passive receivers.
Like little cameras or microphones, yeah.
Yeah.
Just sending raw data up to the brain, which then had to do all the heavy lifting, the interpretation, like, oh, these nerve impulses must mean there's a chair over there.
But Gibson just flips that completely on its head, doesn't he?
He really does. What's so compelling is his core argument. Our senses are active. They're exploratory. Think about it. We don't just see, we look. We don't just hear, we listen. We actively touch. We're constantly seeking out information.
So we're not just waiting for sights and sounds to hit us.
Not usually in normal life, no. Even if something sudden happens, like a bright flash, what do you do immediately? You turn your head, your eyes move, you actively explore it, try to figure out what it was, you engage.
Okay, so what does that actually mean for perception if the brain isn't building reality from scratch?
It means, Gibson argued, that we're directly picking up information, not sensations, but structured information that specifies the environment. It's already out there, meaningful and organized. Perception is detection, not construction.
Information that's already there, how does that work?
Well, this connects to his really crucial concept of invariance. Think of invariance as higher order properties or patterns in the sensory input that don't change even when other things do.
Like what kind of property?
Ratios, proportions, textures, the way things occlude each other as you move. These patterns remain stable even as the raw light hitting your eyes changes constantly because you're moving your head or walking around. They provide consistent information about the permanent features of the world.
Okay, that makes sense. Stable information. So if this information is out there in the light, in the sound, how do we actually grab it?
Gibson's idea was that our perceptual systems, through evolution, have become attuned to these invariants. They've evolved to sort of resonate to this information, to pick it up directly.
Resonate.
Yeah, like a tuning fork resonating to a specific frequency. He even controversially suggested that the specific nerve pathways, like how the retina projects to the brain, aren't really the key to understanding normal active perception. They might explain weird effects in lab experiments where you're passive, but not how you navigate a busy street.
Wow, okay. That's quite a departure.
It is, and one of the most powerful examples he used to illustrate this direct pickup of information is optic flow.
Right, optic flow. This is where it gets really interesting, I think.
Definitely. So simply put, optic flow is the pattern of apparent motion of objects, surfaces, and edges in your visual field caused by your movement relative to the environment.
So it's like the visual world streaming past you.
Exactly. But it's not just random streaming like static on an old TV. It's a structured, lawful pattern.
Mm-hmm.
When you walk forward, things in the center of your view expand outwards, while things to the side move past more quickly. That whole global pattern, that's optic flow.
And this flow, this pattern, is crucial for a lot of things, right? Gibson called it an unfailing index of locomotion.
Precisely. If you see that global expansion ahead and contraction behind, you know you're moving forward relative to the environment. If there's no overall streaming pattern, you're stationary relative to what you're looking at.
So to stay still, say if you're swimming against a current, you'd actually try to cancel out that feeling of flow.
You would, yeah. You'd adjust your swimming to make the visual world appear stable. It provides really precise guidance for knowing your direction and speed.
Okay, so it tells us we're moving. Why else does it matter so much?
Oh, it's fundamental for guiding actions. Steering towards a goal, for one. Maintaining your balance and posture relies heavily on visual flow information. And, crucially, avoiding collisions or timing contact.
Right. Like when something's coming right at you.
Exactly. The way an object looms, the way its image expands in your visual field, the rate of that expansion, the optic flow pattern directly tells you about the time to collision. You don't need to calculate distance and speed. The flow pattern itself gives you the timing information. It's immediate.
That's incredible. And this wasn't just theory, right? Gibson actually applied this.
He did.
Yeah.
During World War II, he did research for the Air Force on pilot training and selection. This was a really practical proving ground for his ideas.
What did he find with pilots?
He observed how the visual world looked to a pilot during landing. As the plane descends towards the runway, all the points on the ground appear to flow outwards from a single point ahead, the aiming point, the target on the runway.
The 0 point.
The 0 point, yeah. And the speed of that outward flow, especially near that point, is directly related to the plane's altitude and rate of descent. Pilots, he argued, were unconsciously using this optic flow pattern to judge their approach and make corrections. They could infer their angle of descent from where that 0 point sat relative to the horizon and the overall pattern.
So they weren't just judging static distances.
Not primarily, no. They were responding to the dynamic flow of information. And what's cool is Gibson realized this analysis worked for any direction of days, not just looking straight ahead during landing. That inverse relationship between the speed of flow and distance holds everywhere. He even drew some of the first diagrams illustrating these flow fields from an airplane window.
Wow, so this practical life or death situation in flying really challenged the old ideas.
Absolutely. The old theories focus on static depth cues, things like size, perspective lines, and a static picture. They assumed a stationary observer looking at a stationary world. But flying is dynamic. It forced the realization that motion itself must contain information. The focus shifted to understanding the stable environment and the flow patterns generated by the observer moving through it.
It's like seeing the world not as snapshots, but as a continuous movie generated by your own movement.
A very informative movie, yes. And optic flow isn't just about your own motion. It also tells you about the shape of things, the layout of the environment itself.
How so?
Well, think about looking at a slanted surface as you move past it. The texture on that surface will flow at different speeds depending on how far away different parts are. That continuous gradient of flow velocities directly specifies the slant of the surface. And an edge, like the edge of a table or a step, that shows up as a sharp discontinuity in the optic flow. The flow pattern changes abruptly. A corner is another kind of discontinuity. These breaks and changes in the flow pattern give you direct information about the 3D structure of the world.
So going back to that example, a kitten peering over the edge of a visual cliff in an experiment, it's likely reacting to that discontinuity in the optic flow.
That's the Gibsonian interpretation, yes. It perceives the cliffness, the edge, directly from that optical information, or a rat navigating a maze sees a corner because of the break in the flow pattern as it approaches. It's incredibly effective information for both humans and animals.
Right. It bypasses needing complex calculations. The information is just there in the pattern.
Exactly.
Now, optic flow is obviously huge for vision, but you said Gibson's theory covered all the senses. He called them perceptual systems.
That's right. He didn't like thinking of senses in isolation. Let's take touch, for instance. He called it the haptic system.
And that's more than just pressure sensors in the skin.
Oh, much more. It includes skin sensitivity, yes, but also feedback from muscles and joints kinesthesis. The haptic system is how we actively explore objects with our hands, our mouths, even our feet. It's about laying hold of the world, as he put it.
So feeling the shape of something.
Yes, but not just passively. Think about identifying a complex object in your pocket just by feeling it. You're actively moving your fingers, detecting edges, textures, its overall shape, its weight. Gibson showed people could identify different kinds of sandpaper just by tapping them with a stylus, or even identify plastic shapes rolled around on their tongue.
On their tongue, wow.
Yeah. It shows the system is extracting information about shape and texture through active exploration, not just registering simple pressure points.
And get this part, I found this fascinating perception of temperature. It's not about the absolute temperature reading.
No, it's about the direction of heat flow at the skin surface. Are you losing heat to the object? Feels cool. Or gaining heat from it feels warm. Your body cares about that relation, that flow, because it's crucial for maintaining your internal temperature.
So cold isn't really a thing in physics terms, just less heat energy. But for our perception, for biophysics, it's a very real signal about losing heat.
Precisely. That's why water at room temperature can feel warm if your hand was just in ice water, or cool if it was just in hot water. Your skin has adapted, its physiological 0 point has shifted, and you're detecting the change in heat flow.
Mind blown.
Yeah.
What about hearing? The auditory system.
Well, again, it's not just about detecting frequencies or loudness. Its main job, exteroceptively, meaning about the outside world, is to pick up the direction a sound is coming from and the nature of the event that caused it, what happened and where.
And having two ears is key for the where.
Absolutely. The system uses the tiny differences in arrival time and intensity of the sound at each ear, covariant information, Gibson would call it, to pinpoint the source location. A single ear couldn't do that nearly as well.
And hearing ourselves.
That's the proprioceptive part, sensing ourselves. Hearing your own voice provides crucial feedback for controlling speech, for modulating how loud you're talking, your articulation.
So hearing isn't just passive reception of sound waves, it's active localization and event perception.
You got it. And even the chemical senses, smell and taste. Gibson argued they're primarily about detecting what the source affords.
Affords, like what it offers.
Yeah, it's invitation quality or demand quality, as he sometimes put it. Is this smell signaling something edible? Is it ripe? Is it a potential mate? Or maybe a predator nearby? It's detecting biologically significant information, not just analyzing molecules.
So survival information, basically.
Very often, yes. Though we can learn finer discriminations, like a wine taster or a perfumer, the basic function is tuned to what matters for action and survival.
Okay, and you mentioned kinesthesis earlier, the sense of body movement. That's not just one thing either.
No, Gibson saw it cutting across different receptor systems. There's input from joints telling you about your body's framework, articular kinesthesis, input from the inner ear about head movement, vestibular, input from skin stretching or moving, cutaneous, and even visual kinesthesis.
Visual kinesthesis. How does vision tell you about your own movement?
Through optic flow. The perspective transformations, the way the visual world flows as you move your body or head, that's direct visual information about your own motion.
It all connects back.
It does. And Gibson's bigger point was that proprioception, self-sensitivity, isn't a separate sense, but an overall function common to all perceptual systems. They all provide information about you in relation to the environment.
So my sense of being upright, for example.
That comes from integrating information from your joints, muscles, your vestibular system, and vision. The visual horizon normally lines up perfectly with your felt sense of gravity because the information from these different systems is covariant. It changes together in lawful ways. That keeps you oriented.
That's a really holistic view of sensing. Okay, so if perception is this active pickup of information, how do we actually get better at it? How does perceptual learning work?
Yeah, that's a great question. It's not just about forming associations like in old learning theories. Eleanor J. Gibson, James's wife and a brilliant researcher in her own right, did seminal work on this.
What did she find?
She showed that perceptual learning is fundamentally a process of detection and differentiation. As we get practice, even with basic things like telling sounds apart or seeing fine details, we get better because we learn to attend to the critical features, the distinctive variations in the flood of information available.
So it's about tuning in better, learning what to look for, what to listen for.
Exactly. She called it an education of attention. You learn to extract more specific, more subtle information that was actually there all along.
So this even changes how we think about something like Pavlov's dogs.
Gibson would argue yes. The dog wasn't just forming a dumb stimulus-response link between a bell and food. It was learning to detect a reliable pattern, an environmental invariant. Bell means food is coming. It detected a signal, a piece of information about its world.
That makes conditioning sound much more intelligent.
More active, certainly. And think about adaptation, how our systems adjust, and how that sometimes leads to illusions.
Like wearing those weird prism goggles that shift everything.
Exactly. When you first put on distorting spectacles, the world might seem to swim or bend when you move your head. The optic flow is all wrong, non-rigid, but walk around for a while.
You get used to it.
You adapt. Your perceptual system recalibrates. Those novel, weird transformations in the optic flow start being interpreted as caused by your own movement through the spectacles, and they stop specifying that the world itself is warping. The information is reinterpreted.
And then when you take them off?
You get the opposite effect. The normal optic flow now feels wrong, distorted in the other direction until you readapt. It shows how flexible and learnable the link between flow patterns and perceived reality is.
It's like that feeling when you've been holding something warm and then room temperature water feels cold.
Similar principle, yeah. An after effect of adaptation. Your system's baseline, its physiological zero, has shifted temporarily.
Okay, but what about those classic optical illusions, like the Mueller-Lyer lines, where one looks longer even though they're the same? How does Gibson explain those if the information is supposed to be unambiguous?
That's a tricky one. Gibson's suggestion was that those static geometrical illusions often play on low-order variables in the visual inputs, simple lines, angles, things from plane geometry. These are bits of optical structure, sure, but they might lack the richness, the higher-order relational invariance found in natural perspective, especially when motion is involved.
So the kind of information in a simple line drawing is maybe impoverished compared to real-world optic flow.
Kinda, yeah. The robust information we use to navigate the real 3D world, especially information derived from movement and texture gradients, isn't usually fooled by those simple line tricks. The illusion happens when you isolate these simpler features.
What about ambiguous figures? You know, the ones that can flip between two perceptions, like the Necker cube or the vase faces picture. Doesn't that contradict the idea that the stimulus specifies the perception?
Gibson didn't see it as a contradiction exactly. He framed it as a discrepancy of information. In a static, frozen image like that, key information is missing.
What's missing?
The dynamic information, the perspective transformations, the optic flow that would normally specify the 3D shape, the slant, the depth unambiguously when you move your head even slightly. Because that's absent in a still picture, the remaining structure can sometimes support more than one interpretation. The light structure itself hasn't changed, but the perceived layout can flip because the information is incomplete or equivocal.
So the ambiguity arises because it's static and lacks that motion-based information.
That was his interpretation. It leads to those impossible objects, too, where drawings look plausible locally but couldn't exist in 3D.
Okay, and what about things like camouflage or those hidden figure puzzles? The information's there, but hard to see.
Right. In those cases, Gibson would say the information for the hidden object is present in the optic array, but it's heavily intertwined with other information. The background texture, the distracting lines, you could call it optical noise. The challenge is whether the perceptual system can learn to differentiate the signal from the noise, to pick up that subtle information. Sometimes it's just really well hidden.
Makes sense. So if the natural environment provides all this information in light and sound, what about human-made things? Pictures, art, writing, how do we perceive them?
Gibson's view is pretty consistent here. He argued that artists, designers, technicians, people who create representations, they are essentially structuring light or sound or texture using the same principles that structure light in the natural environment.
So a painting works because it captures some of the same information structure as the scene it depicts.
Exactly. The information about edges, surfaces, textures, illumination, it's carried by the structure of the light reflecting off the canvas, just like it's carried by the light reflecting off a real landscape. It's the information in the light array that matters, not whether the source is natural or artificial.
That's a cool way to think about art. He even talked about scribbling, right?
Yeah, the fundamental graphic act. He pointed out that when a child, say, scratches a line in mud, they're taking a transient movement, a proprioceptive experience of moving their hand, and creating a persistent visual structure, a trace. They turn their own action into something perceivable by vision. It's linking proprioception and perception.
From making marks to making meaning.
And you can trace this through history, right? From cave paintings capturing animal forms, through sculpture capturing 3D shape, to the development of linear perspective by Renaissance architects, which was explicitly about structuring light to represent edges, corners, and spatial layout realistically.
Perspective literally created information in the picture.
It did. And he suggested the Impressionists were trying something different, trying to paint light itself, capturing the patterns of reflectance and illumination, the perspective of light energy, not just shapes.
And what about movies? Especially things trying to be immersive.
Well, cinema, especially something like Cinerama with its huge curved screen, creates a powerful illusion of movement, vicarious locomotion, he called it. It works because it delivers large-scale optic flow patterns very similar to what you'd experience if you were actually moving through that scene. Your visual system picks up that familiar flow.
But he wasn't impressed with early 3D movies.
He found them often unnatural, yeah. Because while they added binocular disparity information, the slightly different views for each eye, that information was often anomalous, conflicting with other information like motion parallax or perspective cues in the scene. The added depth didn't always fit smoothly with the rest of the visual information, creating that weird, sometimes uncomfortable feeling.
So consistency of information is key.
Very much so, in his view.
Okay, so wrapping this up, we've journeyed through James Gibson's really quite revolutionary ideas, moving away from senses as passive receivers.
Right, seeing perception instead as an active process, actively extracting rich, structured, invariant information that's already present in the environment around us.
And optic flow stands out as this incredibly powerful example. The patterns of visual motion that tell us about our own movement, about the layout of the world, about potential collisions, about shapes and edges.
It's fundamental information picked up directly, allowing us to navigate and interact with the world so effectively.
So this deep dive hopefully reveals that your senses aren't just, taking fuzzy pictures for your brain to figure out later. They're actively exploring, constantly seeking out meaning, detecting these fundamental truths about the world and your place in it.
Yeah, you are fundamentally an incredibly sophisticated information gathering system, constantly tuning into the environment. It's quite remarkable when you stop to think about it.
It really is. So here's a thought to leave you with. If your perception is so finely tuned to picking up information, these invariants, these patterns, what kinds of information, what invariants might you be detecting right now in your everyday surroundings that you've never actually consciously noticed?
What subtle patterns in the light, the sound, the feel of things is your brain constantly, effortlessly picking up that allows you to just be and move and act in the world without even thinking about it?
Something to ponder as you navigate the rest of your day.